sorry for the few minutes late. I was out of battery. So so during this session, we are supposed to complete with Robin to talk about minimal zkVM design. So we are going to do this actually two-stage. I will first talk about, I would say, the way, the things that you can do when you want to design, I would say, a zkVM these days. Generally speaking, like if I want to, I mean, because I built a zkVM like 2 months ago, say, so this is fresh ideas that I have when we want in 2025 to start building a zkVM, I would say, from scratch. And then from this presentation, we will go to the minimal term that Robin may talk about at the end of the slot, at the second half of the slot, we will see. Anyway, the minimal in the sense that when you really want to do only few operations, maybe you have some design decision that you can make that makes the whole thing more efficient. So I'm not here to brag about this current design. Cairo M, anyway, this might be also a bad marketing decision because Cairo M has nothing to do with Cairo. So don't think about Cairo VM if you know it anyway. So I think that so nowadays there is, because I was talking with some people the days before, there is a misunderstanding of the fact that if you actually build a zkVM today, you don't need to commit to the whole execution trace. This is not something that I think it's done currently. So basically, if you go from the execution up to the proving, you have normally an initial, I would say, trace generation, which would be a log of all the states of the virtual machine that you are actually executing, plus a log of all the memory access, I would say, that you have done. So this is sort of too small in terms of number of columns, but very long in terms of the size of the execution table. So this is sort of a first witness generation. And then, from this initial table, you do, I would say, if you talk about data science, you do a group by at some point of these big traces to split it in terms of operations that have been done by the main trace. And this is sort of the second, I would say, witness generation, or the post-processing of the witness, of the initial witness that you have. And this is the table that you actually are about to commit. If it's not clear, you can tell me. But so anyway, the idea is that you don't build a whole trace in the proof element. What you need to think about is you will have several tables that are communicating with each other with a system that you can think about as a messaging system. Like whatever you can push and pull messages from it. The actual way it's done is using lookup argument. Yes, Thomas?
In your mind, what is the advantage of doing this with multiple tables compared to maybe older designs like the old Cairo where you have like the classical way of doing things?
So the thing is that if you keep the whole execution trace is one single table, of course you have the size of the table that is directly related to the size of the execution. So if you want to execute for 1 million cycle or 10 million cycle or 1 billion cycle, then you need to materialize all these tables. But if you actually reshape it, sort of group by in several small tables, you have all of these tables. If you have 10 opcodes, for example, and the execution is sort of evenly split into the 10 opcodes, you have 10 tables, but with the size divided by 10. So that you can sort of fit 10x more operation with the same final log size. And of course the log size influences the size of the proof. I mean the number of columns also influences the size of the proof, but still, so it helps you first get smaller traces, and then also write more easily constraint that applies to given opcode, because you don't need to manage a global state. So the idea is that as soon as you are able to split the main logic into several independent, I would say, circuits, these independent circuits do the operation that they need to do on their own parts, and they remain consistent with each other by sending messages at some point, meaning that, for example, I have consumed the state of the VM with a PC equals something and I, adding to the queue another state that needs to be consumed by someone else, but you don't need to sort of to materialize effectively how the rows are organized with each other. So it's more like, for example, if you say you have a two-opcode addition and multiplication and you're only doing one of the two, each row in your table, for example, for the addition, you enforce that the output is equal to the sum of the inputs, and it will consume a state of the VM, and it will push another state, and this other state might be consumed by another addition, might be consumed by a multiplication, you don't know about it. So it helps keeping everything very local in terms of constraint declaration. And the lookup arguments are used to maintain the global consistency of all these local constraints, so that you actually prove an initial trace, where it's more like you are, instead of keeping the view of the big trace, you are splitting it in independent chunks and sort of building a graph of dependencies in all these chunks thanks to the global lookup argument. Which means that, for example, yes, for a register update, you don't only it's always any operation that you do is always consuming a previous state, so consuming a message that has been emitted by someone else before, and adding eventually something else to the queue that will need to be consumed by someone else at the very end. And at the very, very end, of course, you need to find zero, meaning that the stack of messages, or say a stack of state, or stack of whatever has been pushed by someone else, has been consumed by someone else. Yes?
Is it true to say that the advantage is that the constraints are local to the table, so each table are more appropriate constraints? You don't need constraints that will apply to all the rows, and I think that you gain in this sense at the expense of having to pay maybe for the communication between the different tables.
I mean, it simplifies the constraints in the sense that instead of having to describe all the possibilities in each row, like if you come from the initial Cairo M Design, there are tons of flags, because you need to make sure that if the flags 1 or 2 or 3 is set, then this constraint needs to apply. And this is sort of replaced by independent, very, might be big, but anyway, independent piece of logic that constrains one circuit. So the circuit is sort of the flattened, of course, it's I would say the column of the table is one row is a circuit, and then this circuit just is related to others by pushing to the with lookup argument some part of the value that it uses. So to make sure that they are related to values that have been used somewhere else. For example, if you we can go to memory, but if you want to do memory, like you do an upcode circuit, you need to pull values from memory and then write then values from memory. So from the point of view of the logic of your circuit, the values are here. You just want to constrain the value, like for example an addition. But because it's not an independent circuit, but it's normally an opcode part of a global execution, these values that you use needs to be related to the values that are used, of course, by user component, and especially in this case by the fact that this is a memory segment, one single memory segment normally for the whole. I mean, you can have several memory segments anyway, but let's say one single memory segment for the whole execution. So as soon as you use a value, you need to. So it's really like messaging. You need to think about it as messaging. Yes.
Yeah. So on the point that you were mentioning, you will always be this messaging anyway, even if you were committing to like the execution trace of your program. It's just that if you remove the complete execution trace, which naturally speaking is going to be one of the largest tables that you will have, then you end up having a trade-off of more lookup predictions, but smaller ones.
Yes.
And I think, but you will always have naturally there is this kind of prediction lookup arguments between your tables anyway to ensure like global consistency, because your errors are going to be enforcing only local constraints. One thing, although that I think is worth mentioning, is why more recent VM designs can afford to possibly remove completely the notion of committing to the execution trace is because all the designs were CPU-centric, and your CPU is in a sense literally executing, like reproducing the execution trace. And this is why you had to commit to it, and this is why you had this quite huge burden. This is where approaches like, for example, OpenVM allow these kind of approaches and are in a sense probably more optimal when leaning towards more minimal gaming approaches.
Yeah, I think that's it. 100% agree. So, let's see. That's here. And yeah, anyway, so this is really deciding that you have a messaging stack, and then you can push and pull whatever you want from this stack, and that gives you a global consistency. Thanks to the you have more curves anyway. And then from this point, then you can really decide to add 1 or 2 or 3 or 10 tables regarding depending on the needs that you have. I think that you can have registers, of course. You don't need to have registers actually in the sense that at the very end, the only thing that's required is that the whole queue is empty at the very end. This is the only requirement. So you could even have one single proof system that make cohabit different kind of logics and of state transition function. At the very end, you just need to make sure that all that has been emitted has been used by someone else. I think that this is really the most important thing to have in mind. And so if you think about it like that, you can still, if you think about it like that, so you have one big table that you are going to reshape doing group by logic. And then for each logic, they are constrained. Their constraint is a circuit, so each table is one single circuit. And once you have group by, you're just, from the prover point of view, you start with the group by tables. This is the witness of the prover. And these tables are all related to the initial big data frame because you have the record argument. So which means that you start from a single table, and then you split in several small tables that represent the actual logic that you want to prove. Yes, Stefan?
What is the criteria that you use to create a new table? That means at which point you say, okay, this logic is sufficient enough for me to create a new dedicated table for this logic.
So this is, I think, how I see things now is that if you are from the prover point of view, the constraint that you can describe with the prover library, then you can describe the additive or multiplicative constraint. At the very end, this is the very limited field that you can use when you build the circuit. And then from this you can expose them directly and proceeding with control flow, so you will have to be like addition, multiplication, or you can, if you need to store to have a directional memory, you need also to have the opposite operation like divide, subtraction and division, and then the control flow if you want to have. This is I think the bare minimum that exposes directly what the constraints actually can write if you were to write constraint directly with the prover library. The arithmetic operation plus, if you want to have a VM in mind, some sort of branching call filter, and plus, if you don't have one single table, of course, some sort of memory that needs to live somewhere close to and related to this minimal logic. That being said, I think that, of course, depending on what you want to prove, if you know that you are going to prove most of the time that given computation, instead of keeping only addition and multiplication, you can add an opcode that will gather what should be otherwise a frame of your initial, I would say, of your initial computation. If this makes sense to anyone, it's just like if you expose this minimal instruction, for example, then you write a function that do addition, multiplication, addition again. This is like going to be 5 addition plus 1. You can describe it as a sequence of 5 minimal instructions, but you can say, okay, if I use this frame in terms of computation frame again and again, I'm better maybe just do it as a component itself and get a function that will just go and directly fill this with this energy, but which will save, of course, memory accesses plus cycles, plus eventually operation in the sense that if you do several additions in one component, of course you can reduce the values more, and you can, in one single constraint, have several additions, but the code, usually speaking, have a fixed number. If you define your VM, for example, you will define your addition with only 2 operands and not 2, 3, 4, 5, 10. Yes?
I think to complement on this, whenever you want to prove something, you can start with a single error that's going to be fairly complex, like with a bunch of registers, it will be super wide, but it can represent your whole computation. The problem with this approach is naturally on every row, every step of the execution, you're going to have a bunch of waste, because as you want to represent, for example, all the operations that you can support, only one is going to be executed, for example, or a very tiny subset, and so you end up with like a massive waste on the total area of a layer. And the question of when do you want to offload a part of the computation to a subsidiary air processor, what usually we combines, is basically, I think, looking at the overall surface area of all areas combined. If you manage to reduce this, usually, always depend on like some tricks of the query system that you're using and the different parameters that you're having, but usually reducing the overall air area is going to allow you to gain in performance. Even though there are other tricks, like naturally, if you want to optimize on programming speed only, you would rather have super wide air traces that are fairly small in length. The verifier otherwise, on the other hand, would rather have extremely narrow traces that are fairly long. It's when you have recursion involved, then it becomes a bit more tricky and you have a more complicated trade-off. But yes, I would say surface area of your airs is basically the reason number one in how you design additional chips.
And yes, so for example, if we look at one single simple, I would say, arithmetic instruction, in terms of, yes, in terms of component, you would have, so in the VM, the minimal, I think everyone has agreed that the minimal VM, that is still actually a VM with a random number of cycles, I would say, needs to maintain at least 2 registers, the program pointer to point to the instruction that you want to execute, and consequently the frame pointer, if Maida has this, you were doing this. If you have a read-write memory at some point, I think that it's also required to have, I mean, there might be other things, but you need to have a timestamp that tells when this instruction was used, otherwise you cannot guarantee that the write is followed by a read and not the read and then the write. What are you reading a good value? So that you need also, of course, to get this previous timestamp for each value that you use anyway. And yeah, so basically this is how you locally enforce the global transition by each component actually removing, I would say, from the messaging the previous register state that is actually using, and adding the next step that needs to be consumed by someone else. You don't need to know what will pc+1 be as an instruction, but you enforce at least someone to consume this. And it's the same for, I mean, in my design here, the program is read-only. So for the read-only, you just keep consuming, considering the fact that all the required values have been edited by the segment from the memory commitment. And when you actually read-write, it's the same. For each value of the memory, you remove the previous value for each address, and you add the value that this component is supposed to enforce. And then, and maybe here is where Aki, I understood well saying that it's possible to do something different. I have not figured it myself yet. You need, of course, to run check that you are, in this design at least, that you are writing in the future and you are actually removing a value that's been done in the past. If I'm not mistaken, at least what you were saying yesterday, that it's possible to remove this run check for this kind of operation. No, not you.
I think it was you were not doing this. For the leanVM approach, you can do it.
But because it's read-only, that's what it is.
Yeah, when it's read-only, you don't need any timestamp because the value never change, so you don't care. But even if it's read-write, and if everyone has followed yesterday and have somehow followed, but I did not understand everything, normally it should be possible then to remove this run check. But maybe I actually want to say something that, regarding this, because it's more practical example.
Yeah, I mean, in general, with any of these sorts of arguments, it really just reduces to a matching problem. If you can use some determinism, like log stuff to just deal with that in the most sort of vanilla way. But range checks are something that are like, if they're not too expensive, you can really put those in. But I think there's a lot of work around these techniques already. So if you want, I can grab some resources and put them up.
And the thing that might be also, I think, is, if I'm not mistaken, regarding what you say, if I could remove because here all the clocks, the timestamp, they are guessed during witness generation, so they are not part of the spec. So the prover, when it receives the initial witness, it adds the timestamp to its operation, and then it can make sure that there is sort of a past and a future. Where normally, if you are just talking about local constraint, there is no past and no future. You are just enforcing local constraint at some point, and enforcing that someone else is taking up where you are actually leaving the state. I think that maybe if you want, but you say that you won't have jumps. That's also maybe the.
Those are sort of independent concerns. You can to a large degree reconcile those issues. Just to give you some high level context though on sort of the range check, like the relative power of the range check in this situation. So when you're doing read writes, we found when we were trying to get rid of the range checks, that actually you kind of need a unique identifier for every single one of the matches. So when you start doing multiplicity stuff, so when you start sort of like getting roots with multiplicity, which are just the way we represent them in polynomials, things get kind of well, I don't want to say disgusting, but difficult, because you have to basically, because it all reduces down to the question of whether you're going to be able to sort of check if something is a primitive root of some polynomial. I can go into it afterwards offline if you want. But if you have unique identifiers for everything, you can basically reduce it to like a matching in the same way as lookup. And the way I kind of intuitively think about it is that like you can't really get rid of the range check unless you do like a global check at the end log of stuff. So I would sort of put these things at like a similar level of power in a sense.
I think that this is possible if you have a fixed sort of control flow, and that you exactly know from the very beginning how much time you are going to jump in which location and so on and so forth. So that when you jump, you exactly know the next time it will be used, and this is deterministic from the very beginning. But if you want to have a sort of a general purpose mechanism that allows more flexibility, then you need to have this range check in a second.
Yeah, so like the moment that you allow for determinism, and just to be clear, I mean determinism in the context of there's a unique transcript for every statement data pair. I don't mean determinism in the context of the wrap where we're doing interactions between the prover and the verifier. You actually end up getting way more powerful properties in a variety of different contexts. One of which is, as you said very correctly, this kind of stuff. So you can, the more structure you impose on it, you can sort of pre-process in a way and really get rid of the range checks.
But you know what Robin, what it makes me think about is that in what you can present later on this morning or this afternoon for the repression is the same, because you say that all the indexes are deterministic, and so you even put them as a process column, and you don't need to do this kind of operation, because you absolutely know from the very beginning which indices will be used by which operand and when. So then you don't need to do any kind of checks.
Yeah, because in our model we can even see it as we don't even more. In a sense.
Yes.
On the range checks, one thing that we were doing with Petra, one idea that we had is, so range checks, typically you'll break them into smaller, ranges, like do an 8-bit range check and then sort of do a couple of those to do a 32-bit range check. Most of, you can do a sort of caching type of thing where if you know that some memory cell is going to get read, in close sequence to itself, most of your like the range check on the actual reads can just be in, say, an 8-bit range check. So it only, allows you to read something that was read within the last, say, 256 cycles, and then you have a separate table that sort of loads things from cache. So if basically most of your reads can just do an 8-bit range check, and then if you need to access something that hasn't been accessed in a while, you sort of have this separate table that's just going to do a read and a write. And
so you mean that you sort of have a small read-only memory that is buffered at some point depending on the logic that you are going to use, so that when you need only to read values, you read values from this small buffer, small relation, and then if it's too hard, you need to pull it from the global memory with the regular minus and plus check.
yeah, I think that's right. I mean, reads and writes. It's basically just that, like, when you do an actual read-write operation, it needs to have a timestamp that's within a very small range.
Yes.
Yes.
But for this timestamp difference, what we do, what I've done actually, but we have just implemented the clock update component, which is just not in the VM itself, but on the prover witness generation part, where it actually just figures out when there is deltas in the timestamp that are too big to be handled by the native handshake of the prover. It just keeps adding reads that have eventually never been done by the VM itself, but that helps updating the clock.
Okay, then I think that's very similar to what I'm saying.
Where is the check memory one size? Oh yeah, there is a one size figure that you can discuss as well. Read-write operation, clock update. Yeah, this is just because you have a built-in handshake limit, of course, depending on the maximum size that you want to allow to a prover. And so when you do the witness generation, which is this group by operation, you figure out that there are deltas that are too big. So you can just add this kind of constraint in the table, and they make absolutely no difference in terms of logic. Just keep increasing the clock up until the moment where it will be close enough for the next actual usage in the logic. Yeah, this is really. And so maybe the things that I would like to say. What should I say? I think the memory design is maybe the most interesting thing actually. How to interact with the memory, keeping the memory, what do you do with the memory? Because the instructions themselves are really dependent on the problem that you want to do, apart from maybe addition and multiplication. And I think also that the compilation of the most relevant instruction is something that is interesting to do. That's why I'm so most in favor of the auto-compiled things of what Coder is doing. Maybe yes, one thing I'd like to say is that when you design the VM, so of course the native minimal word is the field element, of the prover. This is what every column will, of course, get one single field element, of course, but from the VM point of view and from the memory management point of view, you don't need to say that the memory word is only one field element, and you can actually instead natively design your memory to handle even a lazy number of field elements, which becomes quite relevant if you want to do native types with several field elements. Like for example, if you are working with a small prime field and you want to implement U32 or U64, you need 2 of them or 4 of them, for example. And actually, you can design your memory component so as to navigate, I would say, this variable size number of field elements per word quite easily. So here I'm talking about that here. So because the main thing that is interesting to notice is that when you do a lookup argument, you actually have trailing zeros that have no impact on the value that you're actually pushing to the, I would say, to the commitment. So it's the same to push memory A0 and 4 value. And you can have an infinite number of trailing zero. It will be the exact same because at the very end, how the lookup is computed is you get the challenges and you do the weighted value of the tuples that you provide with all the random challenges. So all zeros in the tuples are actually discarding the value of the lookups, that if you put all these values at the end, of course, of your tuple, it means that the tuple with trailing zeros will get the exact same value as the tuple with no trailing zero, which helps you navigate easily, for example, between a U16 and a U32 or a U64, if it fits. If it fits, of course, so it's a free casting, I would say, of different size, differently sized unit type.
If I understand correctly, when I read like the paper, if you want, for example, to transform a U32 into a U64, you just add the trailing zero.
Yes, I mean, so you don't, the thing is that because the value that you push to the lookup queue, I would say, or anyway, stack of values that needs to be used at some point, won't be affected by any number of trailing zero. If you are at some point in a use, for example, you are proving an operation of value 32, so the component, of course, has materialized 2 field elements per input, and it does the computation. But if then you want later on to use these values at the same address as a U64, because the U64 then is just adding trailing zeros, you can directly read the memory value at the same address that you computed as a U32, and you read it as a U64.
And is it possible to go in the other direction and removing the trailing zero?
So the thing that there is no real need to either add them or remove because it's from the component point of view. If you are in a U64 component, for example, and then the output of your computation actually fits in a U32, it means that the two last limbs are zero, which means that at this address, later on you can just read in a U32 component, it will match. Because what you want at the very end is just to make sure that all the other terms match. Yes, so you can have variable numbers of limbs per address, which can be quite interesting, both for the instruction set. So you can have instruction with only 1 or 2 fed, but instruction with much more if you want. And for the unit type, so it gives more flexibility to actually play with this. Yes, I think this is. So anyway, the main takeaway to me now that I've done all of this, this is not to jump to the conclusion. So the main takeaway is really when you design the minimal VM, there are actually the operation that exists at the prover library level, which I've said is yes.
Just maybe I have a question on the plus and minus stuff that you did. Is it similar somewhat to the M3 arithmetization stuff that you have done with the streaming stuff, plus and minus?
Yeah, I mean, I consider this type of architecture to be an M3 arithmetization, but I think the idea has popped up a couple different times. But as long as I can, one mental or just a formal model I have for these types of systems, M3, etc., that I think is useful and underexplored is modeling them as colored Petri nets, which is like a well-known type of problem in computer science, and I think that would help us to be able to formally model systems and statements within a language of Petri nets to formally analyze correctness and soundness, and then inherently capture non-determinism. So, yeah.
Okay, yeah, I learned the term M3 yesterday from Ben actually. But yeah, it's probably, when we talk about this, it's probably really, if it's not the same, it's really similar. To be fair, the only, so from my perspective, the idea might come from somewhere, I don't know, but because I've mainly designed all this based on the observation of actually what Starkware is doing for the Stuka prover, and discussion with Starkware engineers. I don't know where they where they pick the idea from, but maybe that the full cycle has been down, I don't know. But that's why also at the very end, you really just need to think that you're pushing tuples, and the fact that it's a logger or whatever kind of argument really does not make any difference. It makes a difference in the cost analysis because then it's how the lookup is actually materialized. It doesn't make any difference in the design decision of the component. Anyway, so what I wanted to say as a conclusion, I think, of the minimal VM thing, I was a bit short before, yeah. So as I mean, my conclusion is also influenced by what you have been doing for 3 years now at Cairo. So I've been long saying that felt-based zkVM was probably more efficient than RISC-V or whatever instruction set already existing for general purpose computation. It would be possible to save on cycles and be at the very end more efficient. Now when I think about this, so I think that you either want to do general purpose computation, and most of the software that we know is actually written with a byte system in mind. Everything is a byte. So in this context, I would put my memory to be from the very beginning constrained to be a byte memory with each file being a byte, and then you don't need to range check again and again all the values because by design all the values are bytes, for example. But then you need to remove completely the idea of a field element from your memory. Or you really want to be at the field element level because you know what you are doing and it's something very specific, and especially, for example, if you are doing a verifier, because the verifier is actually natively, it's one of these programs that are natively field element based, I mean, as far as I can tell. And then, I'm not sure if it really makes sense to do a VM, like a full VM with a full execution flow that can execute random things, because you know that you're about to execute maybe proof verification. And the proof verification, the verifier is determined program. It's not any random program. You exactly know how it will behave, what will be the control flow, how many steps you will do. And then at some point you come up with I would say, a no VM design. There is not even a VM, and then it's very close to, or is what actually Robin will talk either now or either now or this afternoon. But anyway, so I think that the idea is that if you are thinking about field element operation or operation between field element, then you probably can just generate the circuits that you want to do directly as tables that fit your own computation. And this can be done either with a circuit builder or with a compiler compiling a DSL directly to R. I think that most of the companies have R builder actually. For example, if you look at the Start Marketplace, it's definitely not written by, I mean, it's been generated. So that's why also it's a bit difficult to learn with reading Cairo, for example, because it's a machine generated code. So there is a lot of things that you need a bit to remove, to organize, to understand the logic. So I think that, yeah, either you get sort of a DSL or language or model R builder, but it is not a VM then anymore, not so much. Or you can use this for defining precompiles or hash function. Might be a bit easier to work with, but maybe not so much. And if it's general purpose computation, I think it is better to pick an existing instruction set and not to go there so much about defining instruction and control flow and language and compiler and so on and so forth. Yes, so I think this is and I think it's no surprise that actually if you go to end proof, you see that most of the people actually proving Ethereum parts are just using, everyone at the end is using RISC-V, they are still zkVM, and I think only Linear is still using custom circuits for this big program, which is the Ethereum state resolution. So yeah, I think it's just, I mean, I spent 2.5 years building Ethereum software with Cairo, and I think it was a mistake. Yes. So yeah, that's my view about VM, zkVM, and the minimal, if you could say, zkVM. Yeah, I don't know if I should transition to Robin, or if we say that.
If you have like 15 minutes, maybe, I don't know, we can keep on like brainstorming on, I don't know, minimal VM design. We have like 1 hour and a half, so anyway.
maybe some people from Beta, I think they are using a customizer still.
Yeah, and on Petra as well, we were not like, we were using like a customizer. I don't know if you.
Yeah, but
you want
if you
to-
don't think that's the thing.
Yeah, I mean, Petra was a custom ISA. One thing that I think does make it different is it was designed to use write once memory, non-deterministic read-only memory, but kind of like for functional programs, and that does make like a bunch of things nice. So you noted that you can get rid of clocks if you don't have read-write memory, but also there's like the tricks like the prover allocations are non-deterministic, which I think I saw in your design. And I think this like covers a bunch of programs that are like you can express a lot of programs as functional programs. Now the main downside that we found is that when you basically need to do continuations and pass stuff from your local frame into the next frame, you could end up copying a bunch of like data, like local data between these frames, and then sort of redundantly put it into memory. That's I don't know. I mean, I think there's that is a cost. It depends. There's trade-offs. If you can handle memory indirection properly, you can get around it.
It's a good point. We have to copy every time.
Yeah, but I think that the cost of maintaining a custom ISA, maintaining a compiler toolchain or something, whatever, to actually target this compared to the simplicity of just reusing, maybe using 20, 30, 50% of performance, but then being able to focus on places where you probably can get a 5x or 10x if you do a good acceleration or GPU or whatever, then the trade-off is easily done.
For sure. One other idea that we didn't pursue that I thought was like, was thinking about a lot, argument guys recommended building an arithmetization for the zkVM. So Zinc is a virtual machine that comes from the literature, and like ML like languages can compile to it. It's an interpreted sort of small language. So OCaml, the language, has a target. If you run OCaml, there's two compilation nodes. One will compile to native, one will compile to a Zinc-like interpreted VM, and it's a pretty small thing. I think that would be pretty cool, because then you would basically get the ability to write OCaml programs and compile it to Zinc and then productize that. There's probably some more exploration of these sort of like minimal interpreted things that already show up in established languages.
Yes.
That's a big lie from the whole thing.
Does the name Cairo M mean minimal or something?
Yeah, it was a mix of different, the F131 for mobile, because we have focused really on doing technical designing and devices, mobile devices. We have done the campaign because there's a big data set of usage of different 1,500 devices, performance of the Uber and all this kind of things there. Because a mix of jokes like Aero 0, Aero Max, Coca 0, Pepsi Max, or whatever you take. This kind of thing you can imagine. Yes. But at the very end, it's, again, saying that at the very end, I think either build the zkVM or do custom circuits that are possibly compiled with zk DSL or with a model builder. And then generate the chip that you want to use and be focused on your given for them. So I think it makes sense. For example, definitely, I would say love with the zkID and zkLogit. And for this specific use case, I may not choose the RISC-V jet, of course, I may just do the circuit that I want to do. I'm actually using a shape 56R. So you get a shape 56AR plus something that is very custom to the verification, for example, of a JW token. That don't give consistent proof for this operation only. Or I said I want to do a proof of network and I need to be able to prove any program that people want to prove, and I want one single verifier because I'm unchained, and I do VM. This is my rule. So for the Ethereum, I will not do VM. I think that if there is only one thing or few things that are clear and needs to be done that I won't change, then it's probably directly to the circuit that you want to deal with given interaction. Because if there is a circuit for the president to circuit plus the whatever Merkel something probably, and then just play with this, feed the table as you want, and there is no more concept of VM. But then this is what Robbie probably will say for the recursion. So I can drop the mic.